I'm such a loser.
Oh, I say it in all my classes.
I'm gonna go jump in the shower and cry in the corner somewhere.
Somewhere. There's only 4 corners. Don't take it personal. It's just
In that
getting
fetal
out of
position. I failed them all.
No, it's not you. It's my other classes.
Okay.
Honestly, it's Craig's. I've always been. It's my English class. I can't wait. Oh, is that our
I was not good in history until I just realized you just have to memorize a bunch of weird facts that you later, if you really care about it, you'll just go again. Okay, so let's see here. So on the, I mean, not that I don't like history. History is awesome and all. I think I'm gonna have to put some.
that because it's recording.
Oh no, I'm actually gonna say I've been looking into putting math history into my math lessons to make it twice as awesome.
No, please stop.
Let's talk about Leonard Euler.
No.
Leonard Euler is a fantastic mathematician. I don't know. That's my bougie voice.
I say go for it. If it's all on the final, don't do this, then I'm not. I just said it. I'm gonna know.
Okay, so what were the questions? Someone said they had questions. Oh, Peyton, what's
I'm
up?
just kidding, I got 100%.
You just wanted to rub that in my face.
Yeah.
Huh? That's awesome. I'm so proud of you. Last
Use
one.
math late.
It's always the last one, isn't it?
Because the last one's always a word problem.
Why you speak words? Math, you're not supposed to be in English. This one? Okay, cool. Not really. You were just throwing numbers at me?
I did it.
Does anybody want to see this one while it's up?
Oh, yeah.
Sure, right? Why not?
Oh,
You used to call me on the cell phone. Ah! What did I do to myself? Alright, so. Where'd it go? Okay, so let's start like this.
Oh, I forgot I didn't see you.
What's the square root of 100? Square root of 100 is 10. So we're going to get to bring out the whole thing, so 10. Now, looking at that x to the 6th, x to the 6th divided by the index of 2 gives me 3. Any remainder? No, that means I get to bring out x to the 3rd. Okay? Because there's three whole sets of these. Now, if I look at y to the 5th, how many times is 2 going to 5? Twice, with a remainder of 1. So I'm going to bring out y squared, and I'm going to have to leave 1y behind. So there you go. That's it.
why are you talking to yourself?
I'm not, I'm telling you.
It's okay to talk to yourself as long as you don't answer yourself.
Constantly.
Then you're just crazy. People talk to themselves all the time.
I don't.
I kind of do sometimes.
I do.
You can get to this day, just one more hour.
I talk to myself a lot of times.
Right? I think we've had that conversation with ourselves a couple times. Oh, you just twisted that finger.
Well, I'm not sitting down the court like Layla. Okay, we need to get this passed, Layla. Like,
I
no,
already speak English.
this is not what I do. I'm like thinking in my head. Okay, I need to move. Okay, I need to do this. I need to do that. Different.
All right. Let's finish up 8.3 then if there are no other questions.
No.
All right. Where did we leave off at?
Like, do you ever, like,
Oh, is there more notes?
Yeah. I think this is the last one we did, right? 313? Oh, 16? Oh, boom. Okay. Okay, cool. I think we did this one, didn't we? We did this slide and then stopped here? Alright, so do I need to talk about the slide again? Okay, here we go. Simplify products. Simplifying products and quotients of radicals with different indices. So let's start with this right here. We want to simplify the square root of 5.
It's 8.4.
This is the same one, 8.3. It's just the second half of it, because we didn't get to finish it, okay? So, how do we simplify the square root of 5 times the third root of 4?
Well, doesn't the cube to 4? It doesn't, because they're different, doesn't it, right?
Right, the indices are very different, so you can't do that.
Yeah, I'm smart, yo.
Nice job. Oh. Oh, okay. The way it is, you can't multiply them. Now, we can still do something here. And let me show you how this works. Let's see here. If we have... Actually, no, you can't, right? They don't have a common index. You'd have to make it into one. Ooh, that's not nice. That's not the same thing. Okay. So what they did is they took that and they made the same bases on those. So here we go. Let's see. Let me go back real quick. And we have 5 to the 1/2, correct? Right? And then the 4 would be 4 to the what power? 1/3, correct? So the way we can kind of mess with this is by making sure that we get a same root in the bottom, that same denominator. And what is the same denominator here? 6, right? Excuse me. So how do I make this denominator become a 6? I have to multiply the top by 3, right? And how do I get this denominator to become a 6? That becomes a 2. So now I can rewrite this as the 6th root of 5 to the 3rd, and the denominator can be written as the 6th root of 4 to the 6th.
You mean the second?
Sorry, well, yeah, the fourth thing.
Yeah, 4 to the...
Oh, thank you. Thank you. Man, I was doing that yesterday too, huh? Okay. So now I can rewrite this problem, I'll do it right here, as the 6th root of 5 to the 3rd times the 6th root of 4 to the 2nd, which is equivalent to the 6th root of 5 to the 3rd times 4 to the 2nd. It's a lot of fancy math magic.
Wait, can you explain that step again?
Which step?
How 1/2 equals 3/6.
I just multiplied everything by 3. Remember how we can change the denominator? If I multiply by 3, I'd get 6, don't I?
So why do you want that?
Because what we want to do is we want to be able to combine these two radicals.
Oh, with the
So in order
same-
for that to happen, I want to get the same denominator
Okay.
in the roots. Sorry, in the powers. And then you can go from there. Okay. Ba, ba, ba. Which is the 6th root of 2,000 at the end once you multiply this out. Because you've got, what, 125 times 16? Okay. And I think this is the one you were talking about? Pythagorean theorem? Okay. No? Alright, here. Is the distance formula?
Yeah, it was like.
You know Pythagoreans, right?
Yeah, no, it was like, it was not something I knew. Like, okay, I can do the distance formula, I'm not stupid, but it was like radicals. It was like 2 radical 3, and then y1 was like 6 radical 4, and then y, like, it was like something like that.
Okay. Alright. Well, we'll take a look here then. And then we'll go to the questions on the homework. You know, remember which one it was?
It was study plan.
Oh, study plan. Okay. You guys remember good old Pythagoras, right? And his theorem of squares? Okay.
It was a square.
Right. And it really was, guys, interesting enough, a formula about squares. and we were able to take that and apply it to triangles. Because here's what it really turned out to be. I don't know if you guys know the history about that bad boy, but here's what Pythagoras used to do. He used to play around with little squares, and he found that if you put two of them together at a right angle, the area of this, let's say this was, I don't know, 25, and the area here was 16, then he found that the area of a triangle that connected the two would just be the sum of the two smaller ones. Every single time, no matter what. So the area of this square and the area of that square summed up together would always give you the area of that big square. So what, in order to put into a formula, well, how do you find the area of a square? You guys remember that formula? Not the base times height formula, but the side squared formula. You guys remember that? You take a side and you square it. So if you do that, well, they all look the same, don't they? So you kind of had to name the different ones. So we'll call this square A, we'll call this square B, we'll call that square C. So it turned out to be A squared plus B squared was equal to C squared. And this is one formula that's actually been discovered many different ways. Really, really cool formula. But anyways, there's good old Pythagoras theorem. So here, it wants to find the length of the unknown side of each square. So if we take the 14 squared plus the 8 squared, and you guys can do that on your calculator, right? I don't want to well, I don't want to insult you guys by doing this one. Should I do it anyway? Insult me? No opinions? No opinions. Pythagoras theorem. Here's the formula. You're going to plug in the sides. There's your 14 squared and your 8 squared. That equals C squared. Once you do find those squares, you're going to add them. And then to get rid of the C squared, opposite squaring is to take the square root. Therefore, so what they did here is they took the square root of 4 times 65, kind of like that prime factorization, ended up with this. And of course, we know that the square root of 4 is just a 2. That's just a lot of unnecessary work, in my opinion. All they did is simplify the radical at this point. You could do it the way I showed you with the upside down. Okay. All right, cool beans. Moving on. Same idea. Can I skip through these guys? Is that cool?
Can you go back to the first one?
That.
It's 8-3 simplifying radical expressions.
Simplifying radical expressions.
Yeah.
We did that.
Use the distance from
We did simplifying radical expressions.
Yeah, we did it. I just don't get it. Like, we didn't do a lot of it. I'm trying to live with it.
Okay, we'll find some right now. Thank you for saying something. We're good, Britt? Alright, okay, here we go. Cool. Distance formula.
Great.
Distance formula is exactly the same thing as Pythagoras theorem, guys. It's a rip-off. Okay? All they've done is giving you a more I can't say that. A more detailed method of doing it, I guess. Here, let's do like this. Let's say we had some triangle out here, okay? And we'll do something like this. And we'll give this point, we'll call it what, 2, we'll call it 2, 1. We'll call this one 6, 1. And then we'll call this 2, 5. Sounds good to me. Okay? So, this is a right triangle, okay? So my question to you is, what is the length of this base so I can put it in a squared, b squared, right? Doesn't that all have to do? So what's the distance of this segment here? How much is it? How'd you do that? 6 minus 2? Cool, so this is 4, and you went 6 minus 2. And then what's the length of this height here? 4, how'd you do that? 5 minus the 1. There's your 6 minus 2. here's your 5 minus 4. You guys see that? So here's what's happening. They have. Oh, my bad. Yeah, you can't go 5. 5 stupid. So if you had d squared is equal to that distance, which you called 4 squared plus 4 squared, well, how do we undo the square root? Sorry, how do we undo the square? You do square root, right? So that's where this square root comes in from. So it's just Pythagorean theorem, and it's been a little bit more modified so that you can use coordinates, but it's the same thing. Okay? Does that make sense, Brittany? All right, cool. That's the formula. I don't really use a formula. I just do this like I did right now, and I figure out what I need for AB.
That's all it is?
Yeah.
You don't simplify it?
Oh, well, of course you finish it, but I'm just telling you that's where it came from. And I don't think I think I first did it when I was first taught it, and then I never did it again. I always went Pythagoras theorem. I think that's one that they beat into our head with y equals mx plus b, right? All right, so find the distance between those two. So here's how you do. How far apart are those two? 3. That's 3 squared. Plus, how far apart are those two?
4.
That's 4 squared. That's going to give you the distance squared, right? So a squared, b squared equals c squared type thing. So d squared is equal to 9 plus 16. D squared is equal to 25. D is equal to 5. And you're done. Okay? That's how I do it. Gives a whole new meaning to the distance formula, yeah? Any questions on this? Can I change the slide? All right, look at what they did.
They make that shit look harder than it has to be.
Well, kind of, yeah. How far apart are the x's? 3. How far apart are the y's? So you've got this going on. So distance squared is equal to 9 plus 36. Distance squared is equal to, what is that, 45? Take the square root of that. You're going to have to simplify your 45. 3, 15, 3, 5. Got a pair of those. So d is equal to 3 radical 5. You guys like that? Yeah. Thanks. I went through the struggle so you don't have to. Yeah. Cool. Ba, 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 ba. Oh, hey, we're done. Callie, you have something specific you want me to do up here?
I haven't gotten that far yet.
Okay,
I'm
you'll
gonna
let me
get
know.
back to it.